All right. So now we're ready to get into these mathematical tools I keep hinting about. And this is actually, it's going to be a little different for CS, most CS folks. But I want you to try to think about it as a nice change of pace. I find when I step away and do this kind of theory that it's a nice kind of relaxing thing to do. Kind of step away from my computer, just think for a little bit, let things settle in. It's very meditative. So I want you to try to think of it as a positive thing rather than something that's freaky, which a lot of CS people do. But so let's dive into it and see. It's a different way of thinking. I'm going to establish a rigorous way to compare algorithms, which means a way that's satisfactory to mathematicians. And mathematicians tend to go through a bunch of definitions and then proofs, and that's pretty much it. But we have to figure out what is it that we're trying to define here, and how does that help us to study algorithms. So let me start off by defining something called a timing function, which is going to be the amount of time elapsed in some unit of time, maybe seconds, for an algorithm on a problem of size n. That's it. Okay, cool. But does this definition really make sense, or does it? How helpful is it? So there are a few snags if I'm going to try to define such a function for the things I was just looking at. It might be a little tricky because, so first of all, everyone's computer goes at a different speed. My postdoc advisor back at Duke helped me to pay for a really beefy computer. So my computer's probably faster than yours, although maybe it cashed out on the whole GameStop thing, and your computer's actually maybe faster than mine now. But either way, okay, that's annoying. So am I going to have to come up with a different function for each person's computer? Even if I can do that, there are some other problems because it depends on implementation details. So really, we saw that. Really, these two, checking all pairs, these two algorithms are really the same. I was a little smarter in the second one than the first one, but the heart of the idea of the algorithm is the same. I'm going to check pairs. Do I really have the right function, or is somebody a little more clever going to come along and make my function a little bit faster? Okay, so that's how do I know that I even have the right function? Did I do the best I could? And there's another snag. Even if we think we did the best we could, when defining this, we have to ask how long or how much time does each operation take relative to others. So you've probably seen this formula before. This is quadratic formula. Negative b, this is the left root of it. So negative b plus the quantity b squared minus 4ac, all square rooted, all over 2 times a. And the point here is that there are a lot of operations going on, and even in just this one line. The plus, minus, times, and division are much faster than the square root. So that's a bit annoying that I would have to be so careful as I was defining this. Okay, well, how long does square root take on my processor compared to the other one? Okay. And we even just saw a moment ago that even if you manage to nail that stuff down, this is not the only thing that's happening on your computer. It's going to be very difficult to really figure out the true time that these operations take because our computers are doing so many things at once. And even if we can make it do only one thing, even variability in the electricity affects the clock speed and things like that. So gosh, it's just horribly complex to define this thing because we have variability in timing based on things going on in the background. So are we just sort of hopeless? Is there no way that we're going to be able to come up with a satisfactory mathematical definition of time complexity? Well, here's what we're going to do. So we're going to kind of blur our eyes a little bit. Okay, so let me take off my glasses, kind of blur my eyes. And say, well, even if all these things are happening, I can still get like a global blurry view of what's going on. So I kind of blur out this complexity here that's hard to answer, and I can still say something about the behavior of my algorithm. Okay. So for this, we have to introduce something called big O notation, which is more general than algorithms. It's for studying functions, but we're going to apply it to algorithms in a moment. So we'll then apply it to our timing function. So let me dive into that. So I have to define something else now. So big O is a mathematical construct to help us understand blurry upper bounds. This is how I'll say it. So sort of blurry, like what's the worst that can happen of functions. In particular, how does a function scale as we give it larger and larger inputs, ignoring constants and non-dominant terms? So this is not a mathematical definition. This would not be satisfactory to mathematicians. It's not precise enough. But before I give the precise definitions, I'd like to spend some time giving intuition. So intuitively, this would satisfy some of the issues up here. I'm trying to come up with a blurry upper bound. I'm trying to see, okay, kind of like what's the worst it could do, sort of ignoring all these little problems and things that don't affect the dominant behavior of the algorithm. So you might throw in like an extra plus, and maybe that just doesn't make a difference. Okay, that's the idea. Let's now do the precise definition. So our first very precise definition in this class. Big O notation. So we say that a function fn is big O of another function gn if there exists a constant c and a number, really another constant, and a constant n0, so that f of n is less than or equal to c times g of n for all n greater than or equal to n sub 0. Okay, let's look at that. So that's the definition. A function f of n is big O of g of n if there exist two constants, c and n sub 0, so that f of n is bounded from above by that constant c times g of n for all n beyond a certain amount. Okay, so I just said that a couple ways verbally. It still probably sounds like a lot of gobbledygook. So let's look at an example. So let's say that we have a function f of n equals 5n squared plus 3n plus 2. Okay. And let's try to parse this definition and see if we can use it to prove something. So I'm going to make the claim that fn is big O of n squared. Okay. So my claim is that I can find a constant c and n0 satisfying this definition with g of n equal n squared. Okay. So this is my claim, and now the burden of proof is on me to find a constant, these constants, so that I can satisfy the above definition. Before I do that super mathematically, let me just do a little graphical thing here. So I'll say n is equal to np dot a range 6. So let me look at n from 0, 1, 2, 3, 4, 5, and let me say, okay, my f was 5n squared plus 3n plus 2. My g was, it's n squared, but I'm going to claim that if I just pretend that these other terms, like 3n and 2, if I pretend that the 3 is actually a coefficient in front of n squared and 2 is actually a coefficient in front of n squared, then I'm going to choose a constant. So I'm going to choose constant c, which is just the sum of these coefficients. So I'll say c is 5 plus 3 plus 2, which equals 10. Okay. So if I say that my constant times g is 10 times n squared. Okay, so I have to find a constant. And let me just say my strategy is going to be to pretend that these are actually, that this n is an n squared and that this nothing is an n squared. So I come up with a constant of 10, and my claim is that beyond some value, that this is going to be greater than or equal to f. Okay. So let me put my plot legends here. What did I get wrong here? Function object is not subscriptable. Whoops, okay, this is a function legend that takes a list. Okay, fine. Oops, and I need to plot, okay, I need to plot these two separately. Okay, not one versus the other. All right, so what we see actually is that seems like I picked the right constant. I can see at 0, f is actually greater than c times g, but 1 and beyond, it seems like c times g is greater than or equal to f, and that's what we wanted. So the way that we complete the proof is just by noticing. So notice that 3 times n, or really, so what we notice is that n squared is greater than n for n greater than or equal to 1. Or actually, let me say, sorry, what we're trying to prove is greater than or equal. So n squared is greater than or equal to n for n greater than or equal to 1. That's definitely true, right? If I have 2 times 2, that's 2 squared, right? Well, I have 2 factors of 2. So that's definitely going to be greater than 2. 3 times 3, I've got 2 factors of 3. That's definitely going to be greater than 3. Okay, so that's true. So if I replace my 3 times n with 3 times n squared, so first now I'm establishing that 5n squared plus 3n squared plus 2 is certainly going to be greater than or equal to the original. Okay, so that's the first thing. When n is greater than or equal to 0. Sorry, when n is greater than or equal to 1. Okay, but I'm not totally done. I mean, so I found something where, okay, cool, I can combine these terms. Now I've got 2 n squareds. I'm trying to get to a constant times n squared. I still have this nuisance of you know, it's something times n squared plus 2. But then I noticed that actually, you know, similarly, 2 times n is greater than or equal to 2 if n is greater than or equal to 1. And this sounds trivial, right? And this is often what happens in proofs. You write things down that by themselves are so simple. But it's having in your mind that, oh yeah, I needed to establish this fact to establish the whole thing. Actually, sorry, I meant to say 2n squared is greater than or equal to 2 when n is greater than or equal to 1. That's definitely true. So what that means is I can replace, this inequality is still effective if I replace my 2 by a 2n squared. So let me do that. So what I'm saying is the following. This whole thing is greater than or equal to my f when n is greater than or equal to 1. Well, awesome. Now I can actually combine these like terms and say that means that 10n squared is greater than or equal to my f. So yeah, so I'll write the other way. I'll say that f of n is less than or equal to 10n squared when n is greater than or equal to 1. So awesome. We just found our other constant, n0. So we say in this case n0 is 1. All right, cool. QED, proof has been established. All right, cool. So we see that this function is O of n squared. And one of the take-homes here is that this term dominates. So actually these other terms really didn't matter. They came in on the wash. 3n and 2. Compared to n squared, they were nothing. I was able to show I could make them come out in the wash by turning them into n squared terms. Okay. Nice. Now you could come up with a better constant than 10 for this. You could come up with constants that are arbitrarily close to 5, actually. But when you're doing these kind of proofs, you don't need to. Just find a constant that works. Our book shows, I think, a similar example with a slightly smaller constant than I came up with, but it doesn't matter. We're just trying to prove that they're big O, and we've got a lot of flexibility. This is any constant that's a finite number. It could be humongous. As one of my professors in college said, it could be as many or more than there are particles in the universe. Okay, so that's what you're seeing. This is kind of the gap between the mathematical theory and in practice. Like, these constants can be huge. So maybe, I don't know, maybe the algorithm's not useful in practice, but we can at least say it grows as n squared grows. Okay, that's sort of what we're getting through here. All right, so that's the example on a function. I would encourage you to try some more examples to get comfortable with this. But I want to move on and start to examine the algorithms that we did up to this point through this lens. So when we think about algorithms, we tend to think about three things. We think about the best case, runtime. The average case, runtime, and the worst case. And for a moment, let me just think about the worst case in the problem we talked about where we're looking for duplicate elements. I waffled for a second on runtime versus running time. So our book makes a big deal about that, because running time is when you actually look at your wall clock and time things. Runtime is when you can tie it to big O. So these are different things. Running time is empirical. Runtime is in this big O fuzzy upper bound framework. Okay. So I do want to focus for a moment on worst case. I know I try to be optimistic about things in this class, but sometimes it's helpful to be a little pessimistic and think. So if we look at the problem of finding duplicate elements in a list. The naive algorithm said, for all ij in range n, for all I in range n, j in range n. And it's totally clear that, or after you stare at it for a second, you realize that this is going to go through n times n pairs or iterations. Okay, now we're trying to come up with a timing function, and we don't really know how much time each iteration spends because of all these issues that we talked about. But let's just take the worst up the iteration could possibly be. So you're running this on like a computer from the 80s, and it's doing all this stuff, and let's just make that constant a. Okay, so let's assume the most amount of time an iteration can take is some constant a. Okay. And we can make a very large, but look, these iterations are going to finish. It's not like we have an infinite loop or something like that. So they are going to finish. So it's totally legit to choose a number constant a. All right. So that's how we're going to kind of blur things out. So basically what I'm saying is my timing function t of n is equal to a times n squared. All right, that's fine. So let me think I'm thinking about the worst case performance where I actually have to go through every single pair until I find this. And I'm also going to think, in analyzing this, let me think about what's the longest an iteration could possibly take, and I'll call that a. All right. Now this one is compared to the example I showed you a moment ago, it's very straightforward to see that this is O of n squared, because we literally already have our constant, right? Our constant is a. Okay, so that's interesting. What about our improved algorithm, right? So it turns out, so in our improved algorithm, we actually, when we insisted that I be greater than j, it's actually true that we went through fewer iterations. In particular, we went through n times n minus 1 over 2 iterations. Okay. But actually, we could see that this is still O(n) squared. We don't do any better because this stuff comes out in the wash. Because really what we can show is that yeah, it's not going to be possible to come up with a smaller monomial factor than this. Because really, if you expand this, you see that n times n minus 1 over 2 is equal to n squared over 2 minus n over 2. But, you know, okay, so cool. I mean, this is definitely better in practice. Like, you know, we basically cut the pairs in half and actually did even better than that. But remember, this is just a constant. So this is going to come out in the wash. And this is a non-dominant term. So this is something... So even though it looks like this is going to make it faster because I'm subtracting it, it's a non-dominant term. So it's not going to affect how fast this is growing. Okay. So I could write out a similar rigorous proof, but I'm just going to point that out. Okay, let's finally look at the best algorithm we've done so far, which sorts. And I'm going to tell you what T of n is. And we'll actually prove this a little later. But T of n, okay, so there are really two things that are going on in the algorithm. First, you sort. And I'm going to say that takes some constant a times n times log base 2 of n. Okay, so the first step is sorting. Then the second step is looping through the array, which in the worst case, I have to go through the entire array before I find my duplicate elements, right? I could be lucky and they happen at the beginning, but usually I'm going to have to go through the whole array. Okay, so this is my T of n. And so I'm saying, you know, to loop through the array and look for duplicates takes, you know, each iteration of that takes b. And somehow, you know, my sorting is going to take this long. Okay. The claim that I have for the best algorithm so far is that this is O of n log base k of n. Okay, so it actually doesn't even matter what the base is, as we'll see in a moment. Actually, I'll just start with log base 2 to keep things easy. And that this will be true, yeah, so we'll keep the base like that for a second, will be true as long as n is greater than or equal to 2. Okay, so I'm saying I'm going to be able to find some constant, c, and then my n0 is going to be 2. Okay. So to see this, we're going to do a similar thing where somehow what I'm saying is that the n is dominated by n times log base 2 of n. So I'm going to try to come up with a function. I'm going to say that all this is less than or equal to this, but I'm going to replace the n with an n log n times log base 2 of n. And this is true if and when n is greater than or equal to yeah, so as long as I need this to be greater than or equal to 1, so yeah, as long as n is greater than or equal to 2, that'll be true. Log base 2 of 2 is 1. Log base 2 of anything greater than 2 is greater than 1. So that's, the inequality will be true at that point. Okay. One second. Okay. All right. So now I've managed to do this, and you know, I can combine like terms. So I can say, really, what I'm saying is that, you know, my f of n. So I'll just say this is f of n is less than or equal to quantity a plus b times n log n, as long as n is greater than or equal to 2. So now I can see that I have my constant, which is a plus b, and then I have my n0, which is 2. So that proves that this running time is n log n. So what you really see is the dominant operation here is n log n. So the dominant operation is sorting. It doesn't matter how long it takes me to loop through the list once I've sorted. In the sense of big O, the dominant term here is n log n. I mean, I also just wanted to point out that the base of the logarithm doesn't matter because, if I tried to prove log base, 10 of n instead, well, there's this rule of logarithms that log base a of n is equal to log some other log base b of n over log base b of a. Okay, so you can change the bases of your logarithm simply by dividing by a constant, which is the same as multiplying by a constant. So this comes out as constants. But oftentimes in algorithms, we like to think about log base 2 because we often divide things in half. We'll talk more about that. Okay, but now I want you to do a few exercises on Canvas about this just to make sure that it's clicking. And I'll go over one more topic. Okay.